In this video, we're going to continue our discussion of section 6.2 using the normal distribution. In the previous video, we introduced the normal distribution and talked about how we can use normal CDF to find probabilities. We were kind of restricted in the types of problems that we could do, though. All of those problems were between problems. That is, we were given both bounds and asked to find the probability that the variable fell between those two bounds. What do you do if you're not doing a between problem? What if you're asked to find the probability that the variable is less than a number or greater than a number? Well, there are a couple different ways you can handle that, but the method I'm going to push is going to take advantage of the symmetry of the graph and is going to involve either adding 0.5 or subtracting from 0.5, and that's the way I'm going to refer to these problems. I'm going to call them 0.5 plus problems and 0.5 minus problems. And that will be our focus in this video. Let's warm up with a between problem, but we're going to be using this for a purpose. So we're going to be doing a problem using the technique from the previous video, but it's going to lead into the ideas that we need for the 0.5 plus 0.5 minus problems. We used this variable in the last video. The heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected woman is between 60 and 63.6 inches tall. If you were comfortable with the ideas from the last video, you might already know how to do this. You could test yourself by pausing the video now and seeing if you can do it. Okay, either you unpause the video or you just completely ignored me and were waiting for me to do it. Here's how I would do this problem. I see that the problem tells me that the variable is normally distributed, and so that means I'm going to use this bell-shaped distribution to find this probability. Let me draw a bell curve on the next slide. We're told that the mean of this distribution is 63.6. That goes dead smack in the middle of the distribution. And we're told that the standard deviation is 2.5 inches. I just note that off to the side. The standard deviation has something to do with the way that the graph is shaped, but we don't really care where it falls on the axis. Again, this is a between question, so this is what we learned how to do in the previous video, but you'll notice something strange about one of the bounds that I chose. It says find the probability that a randomly selected woman is between 60 and 63.6 inches tall. So 60 is somewhere to the left of the mean, and the upper bound 63.6 is the mean. The area that we want to find is bounded below by 60 and bounded above by the mean itself. We're looking for this slice of area right here. It doesn't matter that the mean is one of the bounds, though. You do the problem the same way. Normal CDF, lower bound, upper bound, mean, standard deviation. So the lower bound of our area is 60. The upper bound of our area is 63.6. The mean is 63.6. So the 63.6 is in there twice, once because it's the upper bound of the area, and once because it's the mean. The mean always goes in the third spot. And then 2.5 for the standard deviation. The standard deviation always goes in the fourth spot. This is a little more than one standard deviation away from the mean, so this is going to be a decent chunk of area. Let's run this in the calculator and get a decent estimate. Second vars, choice 2. If you're running the newer operating system, you'll have the input screen. Lower, upper, mean, standard deviation. With the older operating system, you get this prompt on your main screen. We put in the lower bound, then a comma, the upper bound, which happens to be the mean, comma, then the mean, comma, and then the standard deviation. And again, it's a decent chunk of area. We expected the answer to be smaller than 0.5 because we had less than half of the graph shaded in. Rounding to 3 decimal places, this is 0.425 or 42.5%. So around 42.5% of all women are between 60 and 63.6 inches tall. We're going to use this example as a stepping stone to explain how we do the more complicated problems where we only have one bound. Here's an example. Heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected woman is more than 60 inches tall. Above 5 feet tall. You see that the variable is normally distributed. So it's going to be a bell curve. It's the same bell curve as last time. The mean was 63.6. Standard deviation of 2.5. we're looking for the probability that the woman is more than 60 inches tall, the right of 60 in the graph. 60 is over here, and we're going to go to the right of 60. But we go through the mean. And it didn't tell us to stop at any right bound. It just said more than 60 inches. We have no upper bound here. And that's a problem because normal CDF requires an upper bound. We have to have something to put into that second spot. But here's what we're going to do. We're going to break this area into two pieces. We're going to consider the area on the left side from 60 to 63.6, and we're going to consider the area on the right side from 63.6 on. The piece on the left is what we just did. We found the area from 60 to 63.6. We know how to do that. And the piece on the right we can get from the symmetry of the graph. We know that the total area under the graph is 1 unit. And we know that the graph is symmetrical, so the amount of area on the left is equal to the amount of area on the right. Well, if the total area is 1 and each half has the same amount, then the area on the right must be 0.5. And again, we know how to find this area on the left. This is normal CDF of 60, 63.6, 63.6, 2.5. You might not be able to see that very well, but it's the same setup we used last time because it's the same area. So we're just adding 0.5 to this answer, so the answer is going to be 0.925. We just add these together. When I do this in the calculator, I always put the 0.5 first. So 0.5 plus normal CDF of 60, 63.6, 63.6, 2.5. And again, we already know what this answer is going to be, but let's run it in the calculator just to show you how I would set it up. Pull up your calculator, type the 0.5 plus first, then run second bars, choice 2, lower bound of 60, upper bound of 63.6, mean of 63.6, standard deviation of 2.5, and again we already know the answer is going to be about 0.925 because we already calculated that area on the left, and we get that total area. Let's run through the logic one more time. We can't run the shaded area in normal CDF as is because there's no upper bound. So we broke the area into two pieces. The area on the right is 0.5 because that's half of the graph. The right half is completely shaded in. That area is 0.5. The area on the left I can't just look at and tell you what it is, but I can calculate it with normal CDF because it has a lower bound and it has an upper bound. We had in fact already calculated that area in a previous example, but we ran it from scratch anyway, adding the 0.5 to the normal CDF function and getting the total area. Let's look at another related example. Same variable. Heights of women are normally distributed, mean of 63.6 inches, standard deviation 2.5 inches. Find the probability that a randomly selected woman is less than 60 inches tall. Well, you can probably guess what this answer is going to be if you just go back to the previous result. But let's do this problem from scratch. I see that the problem tells me that the variable is normally distributed, so I'm going to draw a bell curve. The mean is 63.6. Standard deviation is 2.5. 60 lives somewhere to the left of 63.6, and we're being asked to find the probability that the variable is less than 60. Okay, we have a similar issue to last time, but this time we're missing the lower bound. I can't use normal CDF if I have no lower bound. So what am I going to do? I'm going to use the symmetry again, but in a different way. This time I'm going to focus only on the left side of the graph. I know that that total area is 0.5. But I don't want the area of the entire left side, and in particular, I don't want this area at all. I need to exclude this area. Well, how could I exclude it? Well, I can take the area of the entire left side, which is 0.5, and subtract the area that I want to exclude. How does that make things any easier? The area that I want to exclude has a lower bound and an upper bound. That's the issue with the area that I actually want, is that it has no lower bound, but the area that I'm subtracting away does. The lower bound of the area I'm subtracting away is 60. And the upper bound is 63.6. It is in fact that same area that we found in our first example. I'm just going to subtract that away. So normal CDF of 60, 63.6, 63.6 again. It's in there that first time because it's the upper bound of the area that I'm subtracting away, and it's in there the second time because the mean always goes in the third spot, and then 2.5 for the standard deviation. Now we run this in the calculator. I would type the 0.5 minus first, then second bars, choice 2. The lower bound of the area we're subtracting away is 60. The upper bound is 63.6. The mean is 63.6. And the standard deviation is 2.5. And we get an answer that's around 7.5%, and if you compare that with the answer to the previous problem, that won't be too surprising. Let's run through the logic one more time. I wanted just this tail of the normal distribution, right? Just this area on the tail. But that tail had no lower bound because it goes forever and ever to the left. So we considered only the left side, whose area would be 0.5 because of the symmetry of the normal curve. And then we said, well, we don't really want all of that. We just want the stuff to the left of 60, so let's subtract away the stuff between 60 and 63.6. And that's what this calculator function does for us, and we get our area. Now, having only seen one example of a 0.5 plus problem and one example of a 0.5 minus problem, you might still be wondering, well, how do you know whether it's 0.5 plus or 0.5 minus? And my answer is just draw the picture. If you look at the picture where we added 0.5, you can clearly see that we have more than 50% of the graph. We have the entire right side shaded in, plus some more on the left side. In the example that we just completed, we don't even have half of the graph shaded in. We only have a tail of the left half shaded in. There's no way this is a 0.5 plus problem. Maybe that doesn't describe to you how we do the 0.5 minus technique, but it's definitely not a 0.5 plus problem, because if you add 0.5 to any positive area, you're going to get a result bigger than 0.5, and this is clearly less than 50% of the data. It's only that little tail. So you're not really looking for keywords like less than or greater than on their own. You have to put that in conjunction with how the value of the variable you're using as a bound relates to the mean. I'm going to encourage you to draw the pictures. This is why I was drawing pictures in the last video, even though we didn't really seem to need them. I just wanted you to get into the habit of seeing the pictures and drawing the pictures because I thought you would want to do that here. Let's move on to a new variable, and also let's do one where we didn't start with the crutch of doing a between problem first. The weight of crabs caught by a fishing boat is a normally distributed variable with a mean of 609 kilograms per haul and a standard deviation of 125 kilograms. Find the probability that a randomly selected individual haul is less than 800 kilograms. We're specifically told that the variable is normally distributed, so we know that we can use that bell curve for analysis. The mean is 609 kilograms. That goes in the middle of the distribution. The standard deviation is 125 kilograms. We're just going to note that off to the side. And again, the goal is to find the probability that this variable is less than 800 kilograms. Now, a common misconception that students will have when they've only seen a couple of examples is, well, this is a less than problem, so it must be a 0.5 minus. But we don't know that yet. I want you to look at the picture and we'll determine that. 800 is bigger than the mean. So the probability that the variable is less than 800 is going to be the area shaded here. When we look at that area, I hope you can see that this is not going to be a 0.5 minus problem. If you do 0.5 minus a positive area, you're going to get an answer smaller than 0.5, smaller than 50%. But we very clearly have more than 50% of the area shaded in because we have the entire left side shaded in. That on its own is 0.5. And in addition, hint, hint, to that, we have this piece of area from 609 to 800. Now, we don't know how much area that is, but that's where the calculator function comes in. I can find that area because I know the lower bound, 609, and I know the upper bound, 800. So this is 0.5 plus the area from 609 to 800 under a normal curve with a mean of 609 and a standard deviation of 125. By drawing the picture, I see that the less than doesn't tell me that this is a minus problem. Because that bound was bigger than the mean, we actually wind up with more than 50% of the area by going below it. So again, you can't look for just one key word because less than can lead to a plus problem or a minus problem. My opinion is that the best way to do these is to draw the picture. When you look at the picture, you very clearly have more than 50% of the area shaded in. Let's run this in the calculator. 0.5 plus second bars, choice 2. The lower bound was the mean, 609. The upper bound was 800. The mean always goes in the third spot, and the standard deviation was 125. And so the probability that any individual hull has less than 800 kilograms of crab in it is around 0.937 if we round this up. That's 93.7%. Again, the logic here is I don't have a lower bound. We were missing the lower bound. There was no lower bound. So we just took the entire left side. We know that's 0.5 because the total area under the curve is 1 and the left half would have just as much as the right half. So 50% on the left, 50% on the right. And that left us with this piece from 609 to 800, but that has a lower bound and an upper bound. One of those bounds was the mean, and that's a theme you'll notice in these problems. The mean always shows up twice. Once because it's a bound, and then always in the third spot. You'll see that in the other two examples we've done so far. Here it was the upper bound, and then in the third spot. And here it was the upper bound, and then in the third spot. You'll see that in all of these examples. Let's look at another. The lifespan of the females of a certain species of mosquito is normally distributed with a mean of 17 days and a standard deviation of 6 days. Find the probability that a randomly selected mosquito of this species and female lives longer than 3 weeks. This was another exciting science paper that I read for you guys to try to get real-world data, although I found it mildly interesting. They study the lifespans of the females of certain species of mosquitoes because they can transmit diseases. And there's a certain time period that has to pass between when the mosquito sucks the blood of some animal like a bird and when it can transmit that disease to a human. And so if we know how long the lifespan of the mosquito is overall, maybe it won't live long enough to transmit the disease. But this is a real-world problem. They would study the variable because it has to do with the spreading of diseases like malaria, which is a real problem in some parts of the world. So let's find this probability. We're told that the variable is normally distributed. So I'm going to draw a picture. The mean lifespan was 17 days. Mean is in the middle. The standard deviation is 6 days. Kind of note that off to the side. And we're being asked to find the probability that the mosquito lives longer than 3 weeks. You might have noticed how I emphasized the units there. That doesn't mesh with what we were given here. This is in days and this is in days. But the bound we're given is measured in weeks. Don't start at 3 because this is measured in days. 3 weeks is 21 days. And so we're going to be on the right side of the mean. And the question is, what is the probability that they live longer than 3 weeks? So we want to go to the right of that. So we're in another scenario where we have no upper bound. Now, if you look at that picture, I hope you can see we've shaded in less than half of the graph. There's no way this is a 0.5 plus problem. That doesn't explain why it's a 0.5 minus problem, but it's definitely not a 0.5 plus problem, and it's not a between problem because we're not going between two bounds. So that only leaves 0.5 minus, right, by a process of elimination. But that's probably not a good way to teach it. Of course, one could argue I haven't picked the good way to teach anything in this class. So let me pretend to be a teacher and explain why this is 0.5 minus other than process of elimination. The entire right half of the graph has an area of 0.5. But I don't want the entire right half of the graph. There's this piece right here that I want to exclude. We want to exclude this area from the 0.5. So to exclude it, we're going to subtract it from 0.5. And what's so nice about that area that we're excluding? The area we're excluding has a lower bound and an upper bound, and so we can put that in a normal CDF. The lower bound of the area we're subtracting away is 17, which happens to be the mean. Remember, the mean always shows up twice in these 0.5 plus and 0.5 minus problems. The upper bound of the area that we're subtracting away is the 21, the bound, 21 days. The mean is 17. It always goes in the third spot. The standard deviation is 6. And that's how we're going to find the area of that right tail. Okay, so let's see if a significant proportion of these mosquitoes live longer than 3 weeks. This is 0.5 minus second vars, choice 2. 17, comma 21, comma 17 again, because that's the mean, comma 6. And we get about 0.2525, or 25.25%. So a little more than a quarter of the females in this species live. They study the females because they're the ones that suck blood. The males don't live very long. They just die because they don't have the ability to do that. But anyway, that's a pretty significant proportion. So maybe the females of the species have a good chance of transmitting diseases to humans because a quarter of them live a long time. That's the kind of analysis somebody might do with this. So by this point, we've done one example of each of the 5 kinds of pictures that you can wind up with. Let me recap. If you've got both bounds, this is a between problem, and you don't do any 0.5 stuff. Just use straight up normal CDF. If you've got just a tail shaded in, say on the left side of the mean, or a tail on the right side of the mean, these are the 0.5 minus problems. And if you've got a picture where you've got an entire half shaded in, plus some more stuff on the other side, like in these 2 pictures, those are the 0.5 plus problems. So there are these 3 scenarios that you could wind up with, where you've got both bounds, that doesn't require any addition or subtraction, where all you've got is a tail, that's 0.5 minus, or when you've got an entire half plus some more on the other side, that's 0.5 plus. Because the picture tells the story, I think you should draw the picture. Let's do one more. The scores on a placement test are approximately normal with a mean of 53 and a standard deviation of 9. Find the probability that a randomly selected test has a placement score below 40. Okay, knowing that you might ignore me again, try pausing the video and drawing the picture on your own. Okay, let's see what you came up with. I know this is normal with a mean of 53 and a standard deviation of 9. And we want the probability that they score below 40. Below 40 would be to the left of 40. And so we've got no lower bound. Hopefully you got the picture right, and if you didn't get the picture right, hopefully you see what you did wrong. Now looking at that picture, I want you to think for a second whether this would be 0.5 plus, 0.5 minus, or neither. I hope you can see that it's going to require a 0.5 somehow because we're missing a bound. Normal CDF needs 2 bounds. So we're definitely going to need a 0.5. And I also hope you can see that it's not 0.5 plus because we clearly have less than half of the graph shaded in. It kind of looks like this example right here because we only have a tail on the left and we classify that as 0.5 minus. Or you can just think it through. I want to exclude this part right here. So I'm going to subtract that area away from 0.5. And the beautiful thing about the area that I'm excluding is that it has a lower bound, it starts at 40, and it has an upper bound, it stops at the mean. The mean always goes in the third spot, the standard deviation always goes on the last spot. So let's see, 0.5 minus, second vars, choice 2, lower bound of 40, upper bound of 53, mean of 53, standard deviation of 9, and it's about 0.0743. So only about 7% of the scores on this placement test are at 40 or below. So it gives you an idea of what percentile that score is in. That's about the 8th percentile. So this 0.5 plus, 0.5 minus stuff can be a little bit tricky. We're going to see more examples of it in a future video. But if you have any immediate questions, don't hesitate to contact me. See me in an office hour, send me an email, let me know how I can help.